You mentioned manufacturing line
Mm-hmm.
as one application. Some of the things that you talked about are, in my mind, somewhat uniquely enabled by embedded vision. But manufacturing line has been done for years with
yes.
traditional computer vision. Can you talk a bit about how that transition might occur and what might be motivating that transition?
Well, yes. You look at it and you say, well, 3D and a manufacturing side, I'm not going to fool it with a picture. But most bottles are round, and it might be nice to be able to read around. Most flaws could very well be something other than a flat surface.
Mm-hmm.
And you just begin to get more information. And the exciting part of it, just like I said earlier about adding more performance, the company's beginning to play with 3D vision in industrial environments are beginning to find out they can do things they couldn't do before.
Mm-hmm.
And it's just a matter of how much better they're going to be able to do it, what new things can they do now that they could never do before. And so it's just this whole new area to play with.
More generally, even beyond just the 3D specific aspect of it, the migration away from a traditional PC operating system based scheme to a more embedded approach. Can you speak to that a little bit? What some of the motivations are there?
Well, the motivations are pretty obvious, and that is the PC is a wonderful prototyping device. And if you look at the PC as it stands, it doesn't do much at all without the software in it somewhere. And it's got a really nice operating system to make it easy for it to use. When I get to a embedded application, I'm not interested in ease of use.
Mm-hmm.
You know, if I look at my priorities, there are things like size, power dissipation, cost, and you notice I've left performance off. And the reason I've left performance off, that's a check mark.
Mm-hmm.
I either have the performance to do it or I don't.
Right.
And if I can't do it in with a C language, I do it in assembly code. And people kind of shy away from assembly code, but you just think about it. My goal is to get the machine that just is capable of doing the job, because that's the lowest price, lowest power,
Right.
smallest size.
Right. Okay. I'm curious to find out. So I have this idea, and tell me if I'm mistaken. If you look at Da Vinci, for example, that architecture to date has been predominantly defined by what you would call video applications, and now there's this vision opportunity that's blossoming. How would an architecture or products based on that architecture for vision look different than a traditional video or imaging versus video?
I think that's the fun of that question is it may not look any different. It may all be in the software.
Okay.
I alluded to some things earlier, and that is typically when I'm looking at it as a human, I want more pixels. Have you noticed that when you get 1080p, that the picture almost looks 3D versus the old technology? So it's a much better picture. And so I'm working with lots and lots of pixels, trying to make the picture more and more pleasing to the human. When I get to imaging, I may use much, much less pixels, but I'm having to do the whole function of the brain of interpreting what I've seen. But there's still camera in, a lot of processing, and information out.
Okay.
And so, to a great extent, a lot of the same algorithms. You know, the thing I love about digital signal processing in general is basically it only has 4 instructions. If you go back to the very beginning, multiply, add, load, and store.
Right.
And I've talked to our architects at TI for years. How do you keep coming up with new architectures? Just 4 instructions. You can't do many different combinations, but it's all of the system stuff above it, all of the high performance stuff is pretty well, has been the same for decades.
Okay.
And I say that, and I have some professor friends, if they see this, will say, oh, gee, Gene, didn't you hear me? I told you that was wrong. But it is still pretty straightforward. It's just math.
Right.
And so math hasn't really changed a whole lot over the years. But it's the rest of the system of how, now that I have that, do I make decisions?
Okay.
That's a little bit harder.
A question the question I'm about to ask is always fun with a company like TI that has a pretty diversified product line. You have ARM and ARM SoCs, single and multi-core.
Yep, right.
So traditional processors. You have a number of variants of DSP architectures in the product line. You have chips that combine the two in one SoC. Right. Before we talk about other competitors such as x86 and GPUs and other things that
are there competitors?
Well, you tell me. But let's look at your product line first. How has it come to be the case that you have that spectrum of options, and for which, and there are many segments of the embedded vision space, where does one versus the other make sense?
If you look at the diversity of opportunities, requires some level of diversity of solutions. And as we began to see this market migrate from I just need a DSP to I need a system solution, you look at it and you say, I need some sort of a system processor that's going to take care of the real world. And then I'm going to need some processors that take the data and create information. I said in a talk many years ago that the DSP's job is to make data out of the senses, and the processor's job, the host processor, is to make sense out of the data. And so they're doing two different functions. One is getting the data to a point where the processor can make decisions. And so they work well together. They're not competing, they're complementary. And then once you get to that point, is it a small system? Is it a medium system? Is it a large system? Is it a fairly simple control loop but a whole lot of data that I need to compress? Is it a fairly sophisticated decision tree but relatively simple signal processing? So you have all these different choices. Then you get into image processing where you say, I just need an image pipe, or audio processing, all I need is an audio pipe, or communications processor where I need the different aspects of it. And you begin to look at that and you say, these are all different combinations of a relatively small set of things, but when you add them all up, there are a whole lot of different choices. And so you begin to look at it and say, at the end of the day, we probably have 2 or 3 different DSP architectures. We have variants of those architectures, but it's not that many different variants to start with. ARM is, from a high level, they all look kind of alike in the sense that they're all programmed similarly for the ease of the user. But underneath, they're all a little bit different. It's kind of looking at a car and saying every car is the same because of the steering wheel, a brake, and a gas pedal. You say, well, yeah, that's one way of looking at it. Have you looked under the hood? And the hood has different engines. But we don't really talk about that. We talk about the ease of use of the car. I can't innovate by putting the steering wheel in a different part of the car. I have to keep that standard, but underneath things vary, and it's the same way. We're finding that different applications require different kind of performance underneath, but still need the same simplicity from the user standpoint.
Is the distinction at all blur when you have, say, an OMAP 4 with dual core Cortex A9 with Neon SIMD support? Is it at all the case that perhaps an application that might have required a dedicated DSP before, as the CPU becomes more robust, it would evolve, and then the next level of application would move on to the DSP? Is that how it?
Well, you look at that and you do ask that question: how in the world did we come up with the ARM 4 architecture? What is the ARM 5 architecture going to look like, and why is it different from the ARM 3? And you find out that the ARM, or OMAP. Let me get the right term. OMAP is designed for a pocket computer, and that's what it's designed for. And so you begin to look at it and say, well, what are the resources the pocket computer now needs, or the smartphone? And you begin to say, well, okay, now we need 3D video, 3D imaging. We need high quality audio, and you start listening to things, and you just start saying, well, how do I partition my system to optimize for all of these things in a cost-effective solution? Mm-hmm. And sometimes you decide you can move things to the arms. Sometimes you decide the best thing to do is put it in an accelerator. And it really is that ability for an architect to begin to look at it. Now there are two sides of this, and that is when you're architecting a new device, you get all these choices. Mm-hmm. Once the device is firmed up and that's your device, and you're a system designer trying to use it, you have a different set of choices, because now you have to say, I have this set of resources. Mm-hmm. What do I put in accelerators? Well, things that'll fit there. Mm-hmm. What do I stick in signal processors? I stick that there. What can I stick in my my system processor, my ARMs? And how much headroom do I want to leave there for the user to take advantage? Okay. And so you work through all these issues, and you try to level load the processor for whatever you think is important. Is it high performance, the most important thing, low power, finding the smallest device for the lowest cost? What is the real thing you're after for that particular product?
Okay. You made a provocative statement a couple of minutes ago I'd like to go back to. Let's now broaden to look at things like x86 CPUs and alternative architectures like MIPS. Let's look at GPUs. I mean, TI is a Power VR licensee, and it has those GPU cores on some of the chips, and they could be used as a multimedia accelerator more broadly. Let's talk about FPGAs. Where do you see, if any, some of these other processing options playing?
Yes. I find it intriguing on the FPGA. And the reason I say that, I've worked with the FPGA companies over the years, and I was meeting with one of their VPs at one time, and in conversation I said, you know what I find funny is my goal is to design you out. Your goal is to design me out. Our customer's goal is that we don't kill each other because they need both of us. Right. And you just look at it and say the system needs software programmability in the sense of a microprocessor, and it needs hardware programmability. I need some gates to do something for me. Mm-hmm. And so in a lot of cases you'll find that both are necessary. Okay. And as a TI employee, I will tell you that the DSP will always do the solution. You don't need an FPGA. Mm-hmm. Unfortunately, none of our customers agree with it. Not many of our customers agree with us. And that's just the way it is. And that's good competition. Right. I love healthy competition because it makes us both better. Okay. And so I look at the FPGA companies and say they are actually valuable to us. They keep us sharp. They solve some problems we really don't do well. And we actually complement each other better than anything else. Okay. How about, I know you wanted to say a few words about multi-core. Yes. Is now a good time to talk about that? We can. Okay. When I've looked at just the whole Moore's Law activity, I try to tell people that best I can tell as far as performance went or goes, we fell off Moore's Law in the early 90s. And the reason I say that is it was early 90s we started changing our architectures to having deeper pipelines, a lot of cache, a lot of special instructions to compensate for the fact we had deeper pipelines and cache. And so we've got very, very high performance complex architectures. And now we go to multi-core and we decide multi-core means we take 8 of those very complex processors, put them on the same piece of silicon, and take a very complex development environment to make it appear simple. And I look at it and say, what we ran into is our brick wall now is memory. Our memory's not keeping up with our processors. Mm-hmm. Is it time for us to go back and have simpler processors that match our memory systems and just put more processors down? Mm-hmm. Now, for a signal processing task, oh yes, that's great, because signal processing tends to be AMDAL friendly. Mm-hmm. Not so when you look at a lot of the control code that needs still to be low latency, but very, very difficult. Then we need to solve that in a different way. And so I look at it from my vantage point of signal processing, and I would argue that we need to move back to a little bit simpler cores and put more down. We did a multi-core device in the early 1990s that had 1,000 cores on a piece of silicon. Mm-hmm. So we've done the 1,000 core thing. Mm-hmm. Now it happened to be a 1-bit DSP, mm-hmm. but it was aimed at a very specific thing, and that was a NTSC video stream, taking one line at a time and processing it. Mm-hmm. We sold a lot of those devices until digital TV came out, and you didn't need to process it that way anymore. Mm-hmm. And so things changed. But it started with a system problem, and we architected a multi-core. Okay. And so if I look at it, I could be right and wrong, because as long as we look at the proper way to architect a multi-core, start with the problem, and then architect the system to solve that problem, we may come up with, some cases, simpler DSPs or simpler processors with more memory. In some cases, we'll end up with more complex processors but fewer of them, okay, based on what are the system needs. Okay.
You mentioned development tools as a means of sort of hiding the complexity of the underlying yes. silicon architecture. Are there areas of further development that you see, either in a general sense or specific to imaging, vision mm-hmm. type applications that TI and the industry more generally need to focus on going forward?
From a development environment, I think we have to continually trade off the ease of use, the ability to have my golden code, if we still use that term, that I can always use and reuse, and that's generally C, versus how do I get my processing system to be at its best performance at the lowest possible power and cost. Mm-hmm. And a lot of that has to do with, how do I write my code in C? How do I then look for my difficult loops and then go down to a lower level of writing that loop to make it useful? All of that is involved in that development environment, and I haven't even gotten to the point of a systems development environment, because I've kind of left off all the analog, which really is a shame. And the fact I'm now pushing on a lot of the research professors around the world on, I need you, professor, to tell me when is analog signal processing better than digital signal processing. Mm-hmm. And once you've done that, I need you to explain to me what better meant. Mm-hmm. And we're at that junction where we are beginning to look at, how do I move more towards analog signal processing or mixed signal processing, okay, to do the whole system correctly. And that's a difficult environment to do, and so I still see us on the front end of, how do I create a development environment of which I can do my full design, picking the best solution for each aspect of the design, and still not have to do a new integrated circuit, but keep the integrated circuits that are available. Okay. Okay.
How do you see, and again, this may be something of a difficult question to answer, because embedded vision means a diversity of different things, right, but pick a couple maybe. How do you see embedded vision evolving, and how do you see DSP architecture evolving to keep step with the demands of it?
It's like any other aspect, and first off, I always have to go back and say, what did you mean by embedded? Embedded to me, when I was a new engineer, meant a processor of which the end user could neither see nor program. Mm-hmm. And now we look at smartphones and we say those are embedded, except I can program them. Right. And so there's a little bit of, what did you mean when you said embedded? But I think the right answer to that is, there's this whole new world of opportunities that can be standalone, that can do one thing very well, mm-hmm. and let's call that embedded. They're not general purpose in the sense I can do hundreds of different things with them. They do one thing very well. I think there's going to be just a whole new set of opportunities, because what that'll give us is something we couldn't do before. Now we can do it, and we can do it in such a way that it's lower cost, lower power, and does it better. I give a talk on the topic is what's that in your pocket, and it's what used to be in big rooms are now in our pockets. What was the innovation that got it there? Well, the innovation was somebody figured out I needed one in my pocket and convinced me. Technology was the enabler that got it there, not particularly the innovation that got it there. And we can argue that all day long and talk about it, but what it amounts to is, as I can convince myself that I can now do in this size what used to be in this room, then all of a sudden I'm thinking about, well, then I could do this. I could do that. When I think Berkeley many years ago talked about smart dust. And so you begin to think, well, that's kind of dumb. What would I do with smart dust? I don't know. But if you keep that attitude, you'll never know. Somebody said, well, maybe I could paint my wall with smart dust and with a remote control tell it what color to be. Oh, I'd buy that. So there's all of these new opportunities that never existed before. I talk about the clutter around the cloud. And I call it clutter because the more organized you make it, the less innovative you can be. And so I just have clutter. Well, what's the clutter going to do? I don't know. I told one audience that if pet rocks still existed, they'd be tied to the cloud. What would they do? I don't know.
Somebody figured it out.
Somebody figured it out, yeah. But you can begin to create that next level of innovation of, now that I have it and it's small, what can I do with it?
Your definition of embedded is interesting, a dedicated function device. What that got me thinking of is, you look at, and of course TI is a big player in this space, the smartphone space, which is maybe today's version of what the PC used to be.
Yeah.
Do you think that there will continue to be a thriving market for single function devices as the smartphone subsumes? I mean,
Yeah.
I look at GPS, for example. I'm last night trying to figure out how to get around Dallas. Well,
Yeah.
I've got GPS in my phone now.
Yeah, that's right.
There's another one.
And that's a fun discussion to have, and that is, as technology shrinks, will it allow us to do multifunction things, or more and more single function things that are smaller? And I can argue either way. I grew up in the era where the home had a entertainment center, TV, record player, radio. And most houses I remember going into would have one of the three standing on top of the other two, because 1/3 of it had broken, but you didn't want to throw it out. And so you'd have a record player on top because the record player broke first, or a radio on. And you look at that and you say, well, we don't do that anymore. All of our entertainment is component. Why? We're at a point now we can integrate it all. But you don't see many TVs with a DVD player with it. It's just all components. And there's got to be a reason for that. And I think it's the same way with pocket things. We'll find that there will be pocket things that we all want. But I'm not certain that when I get my medical computer that I wear, that I want a telecommunications brand name on it. I think I prefer to have a medical brand name. I think I'm more comfortable with Siemens or GE or one of those as the brand of my medical instrument, rather than Nokia or Motorola. And it doesn't say anything bad about any one of those companies, other than I really would prefer to have the right one. And so I could very well find that my medical computer will be significantly different from my communications computer or my entertainment computer, although I could have them all in the same device.
last question, I think.
All right.
What haven't we talked about? We've covered a lot of ground today. What's specific to embedded vision, perhaps, is on your mind that you'd like to share with the audience?
Well, actually, the things that are on my mind, I won't share with the audience because that's my edge, I hope. But I spend most of my life out talking to what I call the crazies of the world. They're usually found at universities or nearby a university. Mm-hmm. And they're doing strange things that you look at and you say, what are you doing? But they're the ones that are answering that question. What is it going to be in 5 years? What is this new innovation going to be that we've never thought of? And right now, if you looked at it, you'd say that's the dumbest thing I've ever heard. Mm-hmm. And so that's what I'm doing. And for a couple of reasons, I really don't talk much about it. One, because I would be talking about somebody's secret. Right. And two, most people just laugh at me because they'd say that's just dumb. Mm-hmm. Why are you even thinking that? And mm-hmm. so I'm always out there looking for those new dumb ideas. Okay.
Thank you very much for our time today. I really enjoyed our conversation.
Well, good. Yeah. I enjoyed it too, and we'll see what rebuttal we get out of it.
I'm Brian Dipert, Editor-in-Chief of the Embedded Vision Alliance. I'd like to thank you for tuning in and listening to this interview with Gene Frantz. Please check out the other video and other content available on the Embedded Vision Alliance website, and come back soon because we'll have more material coming all the time. Take care.